Okay, so we want to focus on the family of excentral triangles, these blue triangles, to the family of three periodics in the elliptic billiard. Okay, so the family of three periodics in this brown elliptic billiard is shown dashed blue here. Okay, you can see that the elliptic billiard is now upright. The foci, these two brown points, are along the y-axis. But this video is about this derived family of excentral triangles whose vertices over the family, let's see if I can animate them here, whose vertices over the family also sweep an ellipse. Okay, this black ellipse out here. So you can think of the family of excentral triangles of three periodics in elliptic billiard as its own Poncelet family. It has an outer ellipse, okay, with two foci f1 and f2, and it has a caustic, this brown thing, which is the original elliptic billiard, whose foci are shown here and there. Now, one thing we know about this family, actually we know two major things about it. Number one, that the Symmedian point of this family, x6, is stationary at the common center. So it would be stationary here, and this Symmedian coincides with the stationary Mittenpunkt, x9, of the three periodic family in the elliptic billiard. Another thing we know, and it's not germane to this video, is that while the family of three periodics in the elliptic billiard conserves sums, or the sum of cosines, this outer family here, this family of excentrals, conserves the product of its cosines. So if I think of these three angles here, and by the way, this family is always an acute family. It's a family of acute triangles only, whereas depending on the aspect ratio of the billiard, the three periodic billiard family can have both acute and obtuse triangles. But the solid blue, the excentrals, are only acute. Okay, and this is true actually for the excentral triangle of any triangle. The excentral of any triangle is always an acute triangle. So therefore, this family, which conserves, number one, the product of cosines, and number two, maintains the Symmedian point stationary at the common center, is called the family of excentral three periodics. All right. Now, this video is about a very neat phenomenon. I'm gonna invert the. So let's turn off the elliptic billiard original family because we don't need it. But I'm gonna invert the three vertices of this excentral family with respect, for example, to the center of my system. Okay, so let's go ahead and show that. Now when I invert these three vertices with respect to a circle, let's say a unit circle in this case, whose center is at the common center, you get these three new vertices here, and you got this family here. It just so happens, and we've seen this in a previous video that I'm going to show up on the top right, we've seen that the Symmedian of this circle, of this triangle family, this inversive triangle family, is itself stationary. A second thing we saw in the previous video was that when I dislocated the center of inversion to say this focus over here, focus of the caustic, okay, we get a new triangle family whose Symmedian point is also stationary. I'm going to explain to you guys what this dash black line here is in a little bit. Okay, and finally we saw in the previous video that if my inversion point is one of the foci of this outer ellipse, for example this one, I get this other family of triangles with x6, which you may not be able to see here very well. Let's show it. So you get this other family here whose Symmedian point is also stationary. So one conjecture that my colleague Mark Helman made was, what about any point in the plane? What's going to happen to the inversion of my excentral vertices with respect to a circle centered on a generic point in the plane, not the center, not these foci, nor these foci. So let's do this. I now have these controls here, and I can place my inversion point, this P-inv, with respect to, or I can place it anywhere in the plane, right? So let's just pick a generic point like this one here. And this is a triangle that is obtained when you invert these three vertices with respect to a circle centered on P-inv of unit radius, okay? Now I'm showing here for this particular triangle its the current position of its Symmedian point. Let's animate over the whole family, and you notice that that phenomenon, indeed, as Mark predicted, is actually independent of the center of inversion. So if I change my center of inversion and I place it anywhere on the plane, okay, the family that I obtain, this triangle family that I obtain, right, this inversive triangle family with respect to P-inv, will maintain its Symmedian point stationary. And that's pretty nice. So now about this dashed black line. It turns out that the Symmedian point is collinear with the common center and P-inv itself. So that's pretty nice. So X6 star is always going to fall on the segment connecting the common center to the inversion point. So let's move this guy around a little bit. So for example, if I place it here, I get that. If I place it over here, I get that. So you can see that the Symmedian of this new triangle family is completely stationary, and it's collinear with the segment, or with the center, and with the center of inversion. Let's go back to, say, the center position. Here's the center position. Let's go to the top focus in the caustic. You can see that it is collinear. Let's go to the left focus on the outer ellipse over here. You can see that center, and let's zoom in so we can look at it a bit better. You can see that X6 there falls, as we said, on the line that connects the center to the center of inversion, which in this case is P-inv. Okay, if I perturb the center of inversion a little bit to the right and a little bit to the top, that collinearity is maintained. You can see here that this magenta point here indicates the stationary position of my X6. Anyway, guys, this is it. I hope you've enjoyed it. I'll see you on the next video.